Hello, welcome to Chapter 13 on fluids. In part 1 of this video lecture, we will be looking at fluid pressure. So Chapter 13 is broken up into 3 parts. In this first part of the lecture, we'll be looking at the properties of fluids and fluid pressure. Part 2 will deal with buoyancy and Archimedes' principle. And part 3 will talk about fluid dynamics, such as fluid flow, the continuity equation, and Bernoulli's equation and Bernoulli effect. Let's start by talking about an introduction to fluids and look at basic fluid properties. So we start with just a simple review of the 3 phases of matter that we talked about earlier in the course. We have the solid, liquid, and gas phase. So remember that what makes a substance a solid is that the atoms or molecules are rigidly held in place by bonds between the atoms or molecules. So for example, if we have solid water, which we call ice, we have the water molecules rigidly held together. And what this means is that these atoms or molecules can't move around inside of the solid. They're fixed in place. In a liquid phase, the atoms or molecules are bonded together more loosely, and they can actually slip and slide over each other. In other words, the liquid can actually flow. And then finally, the gas phase is when the atoms or molecules are not bonded together at all. They're free to move about, and they only interact with each other when they bump into each other and collide. So let's talk about fluids now. Fluids are substances that flow. And the substances that flow, the 2 phases of substance, are liquids and gases. So fluids take the shape of their containers. That's another way to think about a fluid. If you put a fluid, whether it's a liquid or a gas, inside of a container, the fluid will assume that shape of the container, whereas a solid will just remain in whatever shape it started with. Gases are compressible due to the large spaces between the individual atoms or molecules. So if we think of this gas here, and we learned about the ideal gas law in the previous chapter and so forth, we can shrink this container here and basically force the gas molecules to become closer to each other, and then we increase the pressure of the gas or whatever. But the key thing there is the gas we're able to compress it. So that's what we mean by compressibility. Liquids, on the other hand, are somewhat compressible, but often they're considered to be incompressible. Sort of an ideal approximation of a liquid like water is that it's very difficult to compress water because the water molecules are already very close together. They can slip and slide past each other because it is a liquid, but there's really not that much room in between the molecules for compression. One of the characteristics of fluids that we're going to use is called mass density. Mass density is the ratio of the mass of an object or substance divided by the volume that the substance occupies. So for mass density, in this textbook that we're using, we're going to use the Greek letter rho. All right, it looks kind of like a P, but that's actually a Greek rho. So rho stands for mass density. And mass density is defined as the mass of the material divided by V, the volume that it occupies. So the units of mass density are kilograms, that's the mass, divided by meters cubed or cubic meters, that is the units for volume. So mass density rho is measured in kilograms per cubic meter. So let's just look at a couple examples here. What is the density of water, the mass density of water? So it turns out that water, using the metric system, is very easy to calculate. Water has a density of 1 gram of mass per milliliter of volume. Now, we can do a little more with this to get some sense of this number. Remember that 1 gram is 1,000th of a kilogram, since we typically measure mass in kilograms in this course. A milliliter is the same as a cubic centimeter. Okay, that's an area or a volume about the size of a sugar cube. Now, let's convert that to meters. Well, it turns out that there are 1 million cubic centimeters in a cubic meter. So a cubic centimeter is only 1 millionth of a cubic meter. So we have 10 to the minus 6, that's 1 millionth, meters cubed. And so if you take this number up here and divide it by this number here, you end up with 1,000. So the density of water, this is very surprising, is 1,000 kilograms per cubic meter. So think about this. If you had a 1 meter cube, which would be about this big, all right, and you fill it up with water, and you could think of standing in that, right? It would go up a little bit past your waist. How much weight would that water in that box be? Well, it would have the mass of 1,000 kilograms. In pounds, that would be over 2,000 pounds. So there's more than a ton of water in just a box this big. So water is surprisingly dense. It has a high mass density. Now, something that's even, to me, more surprising is to guess the density of air. Suppose we remove all the water out of this box here and just let it fill up with air from the room. The question is, how much mass of air would be inside of this box? Now, when I first saw this years ago, I would assume that the amount of air in here would be very, very tiny. Maybe a thousandth of a gram or even a millionth of a gram, because we're talking about molecules, right? And we're talking about air that, we basically can't see or feel. Well, surprisingly, the mass of the air inside of this box here would be, and I've got it down here upside down, 1.28 kilograms. So the density of air is 1.28 kilograms per cubic meter. That's almost 3 pounds of air in a box this size. So the amount of the mass of the air in this box is about the same as a heavy textbook. Very surprising. Let's now turn to the phenomena and concept of fluid pressure. So let's do a quick review here of pressure. Remember from the last chapter when we learned about, again, the ideal gas law, Pivnert, we learned about what pressure is. Pressure is basically force that acts on a surface that pushes against the surface divided by the area of the surface. So pressure is force over area, and force, of course, is measured in newtons, and area is measured in square meters or meters squared. And a newton per square meter is called a Pascal, which is abbreviated PA, all right, named after the French physicist Pascal. So we did this example in chapter 12, so I'll just kind of skim through it really quickly here just to see how to calculate pressure. What pressure does a 200 kilogram refrigerator exert on the floor if the bottom of the refrigerator has a size or an area of 1 square meter, 1 by 1 meters? So pressure is equal to force over area. So in this case, the force is the weight of the refrigerator pushing on the floor, which is mg. And we're just going to divide that by its area of its footprint, and that is 1 square meter. So the mass, 200 kilograms times 9.8, and we just divide that by 1, we end up with 1,960 pascals. So now let's turn to pressure in liquids. So imagine this thought experiment here. What if we took a bucket, say, full of water, and we poke 3 holes in it, one at the bottom, one sort of in the middle, and one right near the top where the surface of the water is. The water obviously is going to, squirt out of these holes. What do you think is going to happen regarding the streams of these three streams of water coming out? Are they all going to shoot out at the same speed, or will there be a difference in speed? And if you do predict a difference, what do you think would cause this effect? So think about this for a second, and then we'll talk about what actually happens here. So this is a photograph taken of this actual experiment. It's just a water bottle here with 3 holes, one near the top, one in the middle, and one sort of down near the bottom. And you can see there's a big difference the way the water comes out of these 3 holes. At the top, the water is coming out with a relatively low speed, and the stream of water falls down like this. The one in the middle, you can see, is shooting out at a faster speed, and the water goes a little bit farther. And then at the very bottom, the water is coming out the fastest and squirting out the farthest in distance. So what causes this difference? Well, you might have guessed this. It's due to the difference in water pressure. And water pressure increases with depth. In other words, the farther we go down in this little container of water, the more pressure there is due to the weight of the water pushing down on itself. And so with more pressure down here at this hole, it's forcing the water out of that hole with more speed. So we can now calculate the variation in pressure with depth in any fluid. So it turns out that fluid pressure is due to the weight of the fluid above. And that's why the farther you go down in the fluid, the more pressure there is, because there's more weight of the fluid above pushing down. So what we can kind of do here to calculate this is we're going to, take our container here, our bucket of water or whatever the fluid is, and let's sort of imagine this column here, sort of an imaginary column of fluid, all right, that has a depth of h. We'll use this sort of like height here, right? Really what it is the depth into the fluid. And then over, well, this is sort of a rectangular column, so it has a length L and a width W. And so the area of this column, which is the shaded area here, the area is equal to the length L times the width W. Now we know that pressure is equal to force divided by area. So the force here at this point right here at the bottom of this column is due to the weight of all the fluid inside this column. So that is equal to mg, all right? That's the weight of the fluid inside this column. And then the area of the column, again, is L times W. So the pressure is equal to mg divided by LW. Now, we're going to use the fluid density. Remember that rho is equal to the mass of the fluid inside this column divided by the volume of the column. All right, so we can rewrite this. Instead of saying rho is equal to mass divided by volume, let's solve for mass. So the mass of the fluid in this column from this equation right here, just by rearranging it, is equal to rho, the density of the fluid, times the volume of the column. And the volume of the column is the volume of this, this is a rectangular prism that has a length, a width, and a height. And so the total volume is length times width times height. So I've substituted that for V here. So going back to our initial equation up here, pressure, remember, is equal to mg over LW. So for m right here, I'm going to replace m with all of this here, rho, L, W, and H, all multiplied together. So you can see all of that right here, and then remember it was multiplied by G, and we divide by LW. So one thing we can do immediately is clean this up. Notice there's an LW on top, and there's an LW on the bottom, so we can cancel those. So we're left with pressure is equal to rho, which is the fluid density, times g, the acceleration due to gravity, times h, which h is the distance or the depth in the fluid where we're doing our pressure measurement, okay? So you can see as h gets bigger, the pressure gets bigger. Now, this result here is incomplete because we haven't dealt with atmospheric pressure, which is pushing down on the top from up here. The air, remember, air is a fluid also. Remember, fluids are both gases and liquids. So we not only have to account for the change in pressure with depth here due to the weight of this liquid, but we have to include the weight of the air above it. So let's deal with that next. We talked about gas pressure in the last chapter when we talked about Pivnert and the ideal gas law. So in this particular case, what we're talking about is atmospheric pressure. Atmospheric pressure is due to the weight of the entire column of air above where you measure it. So what this means is if you're down here, standing on the surface of the Earth, the atmospheric pressure that we feel is due to this whole imaginary column of air above us pushing down. And this column, starts where we're at, down on the surface of the Earth, and it goes all the way out into space where there's no more atmosphere. Okay, and one way you can think of it like this: inside of this, column here, down at the bottom, the air pressure is greater, and the atmospheric density is greater because the air molecules are kind of pushed together more. And as we go up in altitude, the air gets thinner and thinner until we reach basically, the top of the atmosphere. Technically, we're in outer space now where there's no more atmosphere. So it turns out that at sea level, which is, where most of us live, near sea level at least, the atmospheric pressure, which is designated as P naught, all right, or P sub 0, is 1 atmosphere, or 1 ATM, all right? That's the abbreviation for 1 atmosphere. Now, what is 1 atmosphere? Well, we learned this again in chapter 12. It's 101,300 Pascals. So this is the atmospheric pressure that you are probably experiencing right now as you listen to this video, unless of course you're listening to it up high in a mountain village or something like that. The atmospheric pressure is going to be somewhat less than this, but we will use this. This is our definition of 1 atmosphere measured at sea level. There's another unit that is sometimes used, and that is the PSI, which is pounds per square inch. And you can see that 1 atmosphere is almost 15 PSI. Now what that means is that the air pressure is pushing on your body with 15 pounds of pressure on every square inch of your body. Now, if you add up all the square inches of the surface of your body, we're talking about tons of pressure from the air pushing on you. So one question that comes up is, why doesn't this crush us? Well, it would, except that inside our bodies, the same pressure exists, which is pushing outward. So the pressure forces are balanced, and therefore there's no net crushing pressure force pushing on our bodies. Let's now return to our calculation of pressure versus depth, and now we're going to include the effects of atmospheric pressure. So in this picture here, this is, you can see we have water or some other fluid here, down here, and then this is the air above it. So in this column here, at the top, we're going to assume that there is no pressure at all because we're basically above the atmosphere. So this is outer space, all right? This is not drawn to scale, obviously. This is the transition where we go from air to water, and at that point, the pressure is equal to 1 atmosphere, which is 101,300 pascals, or about 15 psi. So this is P naught. This is the pressure that you are experiencing right now from the air, and that is the pressure at the surface of any body of water, the ocean, the lake, or even a glass of tea that's sitting on your desk right now. But as we go down into the liquid, a distance of h, that's our depth, then the pressure starts to increase due to the weight of the water adding to the weight of all this air up here. So what happens now is, remember on a couple slides ago, we derived the formula rho GH. That's the pressure due to the increasing weight of the water as we go down. And now you can see all we had to do was add the atmospheric pressure P naught which again is 101,000 pascals. So this is our final equation to calculate pressure versus depth. It's atmospheric pressure, P naught, plus rho GH. So again, at the surface of say a swimming pool or a surface of the ocean, the pressure is 15 psi or 1 atmosphere. I'm going to just use psi here. If you go scuba diving and if you go down, this is actually pretty deep for scuba diving, but you can get certified up to 100 feet below the surface, I believe. That would equate to about a pressure of 60 psi. So notice the pressure is 4 times greater than at the surface. Now, this would actually rupture your eardrums. So what scuba divers do when they dive down is they pressurize their head, the cavity inside their head. And they do this by basically plugging their nose and blowing just to force air into their ears and so forth to balance out that pressure. Otherwise, again, the pressure would be so great that their eardrums would burst. One thing of interest here is when they discovered the Titanic a few years ago, it was down at the bottom of the Atlantic Ocean at a depth of about 13,000 feet. At that depth, the pressure due to the water, it was about 6,000 psi. That's about 3 tons per square inch. So again, that is just a crushing amount of pressure. And that would be fatal to the human body. But interestingly, there are some marine species that can survive those types of pressure, and they do this again by using the trick of equalization. The pressure inside their bodies equalizes the tremendous pressure outside their body. Let's now talk about the direction of pressure. So all of the work that we've done up till this point, we've assumed that the pressure, and we've assumed this correctly, that the pressure is due to the weight of all the water above us. So that sort of gives us this false sense that pressure only acts downward because of all the stuff above us. But that's not true at all, because if it did, there's a couple ways to think about this. If pressure only acted downward, then if we think of some area of water or some little region of water, we can think of this as a small little fluid element, then if the pressure was pushing down on this, it would cause this area of water to accelerate downward, right, by F equals ma. And this would be causing all kinds of currents inside the water. But, if you look at a glass of water, after you pour it and let it sit for a minute, it's perfectly still, right? There's nothing moving inside the water at all. So what that means is that everything in the water is at equilibrium. And so in order for there to be equilibrium, meaning no fluid motion, there must be equal pressure pointing in all directions. Okay, now another way to think of this is if you were laying on the ground and something very heavy was placed on top of you, okay, let's say somebody sets let's say like a couch on top of you, right, while you're laying on the floor, all right? Well, what's going to happen there? Well, the couch's force is obviously pushing down on you, but you don't accelerate downward because there's a force pushing upwards from the floor. So you actually you're feeling an equal force in both directions, all right? And so that's sort of an analogy of what's going on here with pressure. That pressure is coming from all directions equally. For a very, for if we take a small little sample of fluid here, all these arrows are the same length and pointing in opposite directions. So there's no net force on this point right here. So at any point, fluid exerts pressure equally in all directions. The results on the last slide with the direction of pressure being, equal in all directions leads us to another principle of fluids, which is called Pascal's principle. And this also leads to the idea of hydraulics. So Pascal's principle states that pressure applied to a confined fluid increases the pressure everywhere in the fluid by the same amount. All right, so that means if we have a container of fluid and we somehow try to increase the pressure at one part of that, inside that container, that pressure is going to instantly or almost instantly equalize and spread out so that the same pressure is seen everywhere in that container. Now, again, we have to be a little careful here. We're ignoring the effects of the increase in pressure with depth, but if we just sort of put that aside, Pascal's principle states that if we apply pressure over here, that same pressure has to equalize and be felt everywhere. So this, and by the way, if there were a pressure difference, in other words, if Pascal's principle didn't hold, the fluid would be in non-equilibrium and it would move around until that pressure actually equilibrated and became the same everywhere. So let's take a look at this example. This is an example of a hydraulic lift, and you may have seen something like this in a mechanic shop to lift a car, to do work, for example, changing oil, any kind of work that's done underneath the car. They often use a hydraulic lift like this to push the car up. And surprisingly, this what powers this hydraulic lift is not some huge, powerful engine or motor. It's usually a tiny little pump that increases the fluid pressure over here. So what you can imagine is, remember, in the last chapter, chapter 12, we learned about pistons inside of cylinders. So imagine that you can push down this red piston inside of this thin, narrow cylinder here. So we're pushing down with some force F1, and let's say the area here, the cross-sectional area of this pipe here is A1. So the pressure over here, remember, pressure is force divided by area. But according to Pascal's principle, we have to have the same pressure everywhere inside this fluid. So over here, we have a much, much larger area. All right, this is A2, and here's the force F2. So if the pressure is the same here as it is over here because of Pascal's principle, then F1 over A1 must be equal to F2 over A2. So let's solve this equation here for F2, the force on this big, wide, large area piston. So F2 is equal to A2 over A1 divided by F1. Now notice, so we have F2, the force 2, this force here, is equal to this force multiplied by the ratio of those two areas. This is an example of a force multiplier. And this area here of this piston, remember, area goes as the square of the radius. So this piston here may be 100 times larger in area than this little piston here. So what that means is this force here is going to have to be 100 times stronger than this force in order for Pascal's principle to apply. So think about this. If we push down right here with a force of, let's say, just 30 pounds, all right, you could do that with pushing on this with one hand. You could push down with 30 pounds of force. What force is this over here? Well, remember, if this ratio is 100, then this force here is 30 times 100, which is 3,000 pounds. That means by pushing down here with your hand with 30 pounds, you can lift up a 3,000 pound car over here. This is the idea of hydraulics and how hydraulics work in industrial equipment and construction equipment. So we're finally at the last slide of this video. And here I'm hoping to prove to you that physics doesn't suck. So some of you by now in this course are probably thinking that physics really sucks. All right. I've heard it. I've heard the rumors. I've heard the murmuring in the hallways and so forth. Well, let's think about this literally. Does physics or can physics actually suck? So one demonstration, I usually do this in class, but you can do this at home, is take a water bottle and after it's empty, so before you throw it in the recycle bin, suck all the air out of the water bottle. And it's very easy to get the water bottle. It'll just basically crush itself like this, okay? And so, you may be thinking, all right, by sucking the air out of this water bottle, there's some sort of suction force that's crushing this bottle. Another example is if you have a drink out of a straw, all right? You're sucking on that straw, and you may be thinking that this suction is creating some kind of force that pulls, the lemonade up the straw into your mouth. Another example is the so-called suction cup, right? It's sucked onto the surface that it sticks to. And then, of course, a classic example of sucking, right, is the vacuum cleaner. All right, the vacuum cleaner, we think of it sucking up dirt from the rug. Well, in all cases here, this is a completely incorrect interpretation of what's going on. In all of these cases, there is no sucking. It is always pushing. It's air pressure pushing. So when we, so-called suck the air out of a bottle like this, all that's happening here is that we are removing the air from inside the bottle. Remember, the air pressure outside the bottle is 15 pounds on every little square inch of this bottle. So by removing all the air from this bottle, we are actually producing probably hundreds of pounds of force on this bottle, and it just crushes flat. All right. The same thing when you drink from a straw. What's happening here is you're reducing the pressure inside of the straw, so the atmospheric pressure out here is pushing the liquid down and up through the straw. A vacuum cleaner, what basically the engine or the motor pump, the air pump inside the vacuum cleaner, is creating a low pressure region so that the outside air pressure out here is actually pushing the air and the dirt into the vacuum cleaner. There is no such thing as a suction force, and hopefully, my friends, I have just proven to you that physics does not suck.